Welcome to my attempt at an introduction to modeling with differential equations. Hopefully a short introduction, even. In my experience, differential equations have the worst reputation as a part of math that is painful and ugly and difficult. While it's true that there are definitely plenty of models involving systems of differential equations that are very complicated, but they aren't all, and it doesn't have to be painful. So what I want to try to do is give you at least the vocabulary to recognize different kinds of differential equations, so that if they're not of a simple variety that you know how to solve, because I'll show you some of that, you'll at least know how to look for help, so that you know what kind of a beast you're dealing with. So first I want to talk about some of the different flavors of differential equations, some different kinds, and then after that I'll go over some techniques for simpler differential equations that you will run into all the time, that you really should know. So first of all, what is a differential equation? Right? A differential equation, or a difference equation, is basically any equation involving a derivative. So in continuous time we call them differential equations, in discrete time we call them difference equations. So a typical one, dn by dt is equal to r times n at t. That's a differential equation because it involves the derivative of n. A difference equation would be delta n over delta t is rn at t. The only difference between these two is that over here t only takes integer values, and here t could take any value. Oftentimes manipulating difference equations is more difficult, or there are more tools for manipulating differential equations, so we'll tend to take discrete time models and turn them into continuous time models just for the sake of analysis. When we talk about differential equations, we often talk about the order of a differential equation. We'll say first order differential equation, second order, third order, whatever. Those all just refer to the order of the highest order derivative in the expression. So the order of the highest order derivative. So if I had d squared y by dx plus dy by dx minus x equals y, that's a second order differential equation because it's got a second derivative of y in it. If I had a third derivative of y, there would be a third order differential equation, so forth and so on. We talk about whether our differential equations are linear or nonlinear. So linearity. This is a little bit harder to parse into words, but it's linear if none of the y terms, I put y in air quotes that you couldn't see just then, none of the y terms are multiplied by other y terms in a linear differential equation. None of the y terms are multiplied by other y terms. So for example, this one up here is a linear, this is a second order linear differential equation because none of these y terms are multiplied by any others. But if I change it and I say this one is y times dy by dx, suddenly this is a nonlinear second order differential equation because you can't separate these y terms from each other. It makes it a nonlinear term. And whether or not your model is linear changes what tools you can use to analyze it, so it's an important distinction to remember. Ordinariness is another thing we talk about with differential equations that I've always thought was kind of funny. An ordinary differential equation, a differential equation that is a function of one independent variable. So again, the one I wrote up here, that's an ordinary differential equation because all of the y terms are a function of just x. Most population models, most simple population models are going to be ordinary because population size is just a function of time. If you have a differential equation that's a function of multiple variables, then it becomes a partial differential equation. So that's a differential equation that is a function of multiple variables. Much like a partial derivative, right? If you have a function of multiple variables, you don't have a single derivative for it, you have a bunch of partial derivatives. Then you need, if you have multiple independent variables, then you end up with a system of equations because you need a partial derivative to describe them both. Right, so that's an example of what a system of partial differential equations might look like. I've run out of room here, so a system of differential equations is just a set of functions that are all functions of the same set of independent variables. So I might have two different equations that describe, say, the number of predators and the number of prey organisms in a system, and if those two functions, the function for the number of predators and the function for the number of prey, if they depend on the same set of variables, then that makes that a system of differential equations where the same set of variables determines equilibrium for both functions. You can have a system where there's multiple functions that all depend on the same single variable, or they can all depend on the same set of variables. In fancier models, people talk about whether their DEs are homogeneous or not. So homogeneous differential equations are a subset of differential equations where the sum of a set of solutions or multiples of solutions are also solutions. So homogeneity or non-homogeneity just says something very distinct and about the set of all solutions mapping back onto itself. And the last thing I want to mention is separable or separability. A differential equation is separable if you can easily manipulate it to get the dependent variable and the independent variable on separate sides of the equal sign. So separable differential equations tend to be really easy to solve. Most of them in the real world aren't separable. So separable equations, you can manipulate them to get dependent and independent variables separate. So like all the y terms on one side and all the x terms on the other. So those are pretty much all the jargony words people use to talk about differential equations. So if you know what they mean, then and you encounter them when you're reading a paper or someone's talking about a model, it won't sound as much like total gibberish, hopefully. So let's talk about actually using differential equations. So let's say we've built our model and so we've got our differential equation. I'm going to start with a really simple one. Let's say we know that dy by dx is equal to x squared minus 1. If this is my model for how something defined by y changes with x, there are three basic things I'm going to want to know about how this differential equation behaves. You might want to know the general solution, which is just given some expression for the differential, what is y? If we solve the differential equation, that means finding an expression for y at all values of x. It tells us how the model behaves everywhere for all time. for simple differential equations like this one, which is separable first order differential, linear first order differential equation, I can solve this one by just first separating the dy and the dx like so, and then integrating both sides. Which gives me y is equal to 1/3 x cubed minus x plus c. So that's my general solution to that simple linear differential equation up there. If I want to have a particular solution, I need to have another piece of information. I need to know the value of y at some point so that I can solve for what c is. So if I know, say, that y at x is equal to 1 is 1, then I can get a particular solution, which is that y is equal to 1/3 0 minus 1 is equal to c, plus c, rather. So c is going to be equal to 2 minus 1/3, which is just 5/3. So given this condition, my particular solution would be y is equal to 1/3 x cubed minus x plus 5/3. So let's look at a maybe more interesting differential equation, the logistic equation. So in logistic population growth, the change in the number of individuals over time is r times n at t times a density dependence term, 1 minus n at t, over k, the carrying capacity. So the first thing we might want to know is to find a general solution. And we have a whole video about that elsewhere, so I'm not going to do it for you here. It might be a good exercise, though, since this is a slightly more complicated solution to find. So the second thing we want to know about our model, and the most frequent thing you're going to want to know about your model, is where the equilibrium points are. Right? Does your model have an equilibrium? Is it going to settle down to some steady state over time? And where is that going to happen? So what is an equilibrium state? Well, it's a state where if you start the model there, it won't change. So basically, if dn by dt is equal to 0, that's an equilibrium point, because if you start the model there, or if the model gets there, it won't move. So if you want to find your equilibrium points, you just set your model equal to 0 and solve for the value of n where that equilibrium happens. So if we do that here, we say, okay, 0 is equal to Rn, I'm just going to drop the t for now, 1 minus n over k. So we can see just by looking at this that we're going to have two equilibrium points, one at n is equal to 0. Anything that's an equilibrium point, I'm going to put a hat on it so you can tell the difference between n and the equilibrium n. There's another equilibrium at n is equal to k. In more complicated models, your expressions for equilibrium points might not always be so simple, but the procedure is always the same. Set your original differential equal to 0, solve for values of your dependent variable that satisfy the equilibrium condition. So once you've found your equilibria, this last thing we care about for our model is, are those equilibria stable? So, stability. What do I mean by a stability? So if you think about your model, if we start the model at the equilibrium point, it won't change. N will stay at whatever the n is of the equilibrium point. When you're thinking about stability, imagine what happens if your model is really close to the equilibrium point. If the equilibrium is stable and you nudge the system away from it, it's going to go back to the equilibrium. If the equilibrium is unstable, that means that if you nudge the system away from the equilibrium point, it's going to keep going away from it, and it won't go back to equilibrium. Now, I'm going to take my original function, and I'm going to call it something else. I'm going to call it f as a function of n now. Is Rn times 1 minus n over k. This now is the description of how this derivative changes with n instead of with t. So the derivative of this function, df by dn, is just r minus 2rn over k. And the stability of my system at equilibrium is dependent on the value of this expression at the equilibrium point. So what does this tell us? Basically it means that if the value of this function is negative, it means if you try and increase n, the change in n will be negative and it'll go back to the equilibrium. If it's positive, that means if you go away from n, you'll keep going away from n, and the equilibrium is unstable. So, if it's greater than 0, it's unstable. If it's less than 0, you have a stable equilibrium. So for the logistic, at the n is equal to 0 equilibrium point, df by dn is r minus 2r times 0 over k, which is just r. So if r is less than 0, the 0 equilibrium is stable. If r is greater than 0, the 0 equilibrium is unstable, right? Obviously, because if you go from n is equal to 0 to when n is equal to 1, and r is greater than 0, then your population is going to start growing, so it's not a stable equilibrium point. But if your population starts at 0, and you perturb it, you go a little bit away from equilibrium to n is equal to 1. If r is negative, you're going to go right back down to population size of 0, and that's stable. For the other equilibrium point, n hat is equal to k, df by dn is r minus 2r k over k, which is negative r. So in this case, if r is greater than 0, the equilibrium is stable. This also makes sense. So for the n is equal to k equilibrium, if you bump the population down a bit lower than k, and the population is growing, it'll bump right back up to k. So k, that makes k stable. But if r is less than 0, and you bump the population away from k, it's going to keep shrinking, so that k is unstable. So for any kind of differential equation model, those are the 3 steps, or the 3 kinds of analysis you might want to do. You might want to find a general solution, you might want to find where the equilibria are, and whether they're stable. And if you're lucky, it'll be relatively straightforward to do, like it was here. So now that we've looked at a simple and a slightly less simple one-variable model, I'm going to look at one simple and one less simple multivariable model. So in my simple multivariable system, instead of just having an expression for the rate of population change for one population, I'm going to look at 2. I'm going to call N1 is the number of bacteria with genotype A, and I'm going to call N2 at T the number of bacteria with genotype B. So I can model this system with 2 differential equations. So I get the change in N1 with time, and I'm going to say that it's A times N1 plus B times N2. So that makes this the division rate, and this lowercase b is the mutation rate from capital B to capital A. So the overall change in the number of N1 individuals is going to be a function of how often existing N1 individuals divide and how often existing B individuals mutate. For the other population, same thing applies, dn by dt. We say C times N1 plus D times N2. And this time C is mutation from A to B, and D is the division rate of N2 individuals. So that's a fairly simple linear model of evolution in bacteria with mutation, forward and backward. I'm going to skip the general solution part because it's not actually that interesting in this context, but it's fairly straightforward how to do. And skip straight to finding the equilibria of the model. So because this is a simple linear system, we can rewrite it in matrix form. That's why linear algebra is called linear. So the first step in finding the equilibrium and its stability is going to be rewrite this. Now dn1 by dt and dn2 by dt is a vector, and we can write it as a matrix times another vector, where this vector is going to be just n1 and n2, and in the matrix we have these coefficients, a, b, c, and d. And you can just check for yourself that that multiplication does work. So to actually find the equilibria, you can either use matrix magic to find it, or we just know that we need to find the points where dn by dt, dn1 by dt is equal to 0, and dn2 by dt is also 0. And they both have to be 0 for the joint equilibrium to exist. So to find points where those are both 0, first we find the condition for n1 being 0, which is that an1 plus bn2 is equal to 0, which means that n2 is going to be equal to minus a over b times n1, and we plug that back into the equation for dn2 by dt, and we figure out that the only equilibrium point, n1 hat is equal to n2 hat is equal to 0. And in fact, for any linear system, the only equilibrium point is going to be 0. The question is that equilibrium point going to be stable? And actually, I almost lied to you. So usually the only equilibrium point is 0, 0 in a linear system, unless the determinant of this matrix, if the determinant, let's call it m, is equal to 0, then you have an infinite number of equilibria. But that's fancy. It's still something you should be aware of. So to find the stability of our equilibria, we go back to this matrix, the matrix of coefficients, which were a, b, c, and d. So I'll just straight up start off by telling you that the stability condition is all of the eigenvalues of m have negative real part. Right, because eigenvalues can have real and complex parts. So as long as the real part of all the eigenvalues of m is negative, the equilibrium at the equilibrium point, then the equilibrium is stable. And you can find those eigenvalues by solving the determinant of m minus I times lambda equals 0, right? And those lambda will be the eigenvalues. So why should that be true? Well, recall for any eigenvector, m times some vector is equal to lambda times some vector. So in the long term, the eigenvalues tell you whether the system is growing or decaying in the direction of the eigenvector. So if all of the eigenvectors are negative, that means our vector of n1 and n2 is going to be shrinking back towards the equilibrium point of 0, 0, decreasing, if all of the eigenvalues are negative. So if all the lambda are negative, the system always decays back towards the equilibrium at 0 and 0. I have two other things to say about this. Asterisk points. If the eigenvalues are complex, if the real part is negative, then the system is stable. But if the complex part exists, then the system will cycle towards the equilibrium. Oscillate, I should say. Towards the equilibrium. It's still going to go to the equilibrium, and the equilibrium is still stable, but instead of heading straight there, it'll kind of spiral around it until it gets there. And the other asterisk point is that in the discrete time case, the stability condition is actually that the eigenvalues are all in between 1 and -1. Or if they're complex, that the square root of a squared plus b squared is less than 1. So while we're on the subject, as an exercise, for the model we just talked about, dn1 by dt and dn2 by dt is equal to a, b, c, d times n1 and n2, find the conditions for stability. Of the equilibrium point. So by that I mean solve for expressions for the eigenvalues, of which there should be 2. What values of a, b, c, and d make sure the eigenvalues will be negative. Remembering that to find the eigenvalues, you need to solve the determinant of m minus I times lambda, and that m equals I times lambda, and that the matrix m minus I times lambda is going to look like this. A minus lambda, b, c, and d minus lambda. For my last trick, I'm going to show you a really commonly used tool for finding stability of equilibria in multivariable nonlinear models. So everyone's favorite nonlinear models are epidemic models. So we're going to start with a two independent variable, So I'm going to start with a system with 2 equations describing the changes in the number of susceptible individuals and the number of infected individuals in an epidemic. So you may have seen this before, you may not have, but here we go, we're going to try. So ds by dt, the number of susceptible individuals in my population, is going to change according to this ugly thing, theta minus d times s minus beta times s times I plus gamma times I. So, beta is the So this is a pretty standard model. Beta is the transmission rate. How often do people who are infected infect other people? Theta is abortin, it's the immigration rate of new uninfected hosts. So that could either be people who are just showing up not infected or people who are being born. D is the background death rate of things other than the disease that we're modeling. And gamma is the rate of clearing. So how often do people who are sick get better? Rate of clearing by immune function. And the number of infected individuals over time is going to change according to beta times S times I minus all of these forms of death, D plus V plus gamma, all times I. I'm going to do one. So V is the death rate due to the disease. So let's look at these for a second. S is going to increase by the rate of immigration. It's going to decrease by the number of people who are susceptible who die, D times S. The number of susceptible people is going to go down by beta times S times I, which tells you how many susceptible individuals are going to get infected by transmission from infected people. And it's going to increase by gamma times I, which is the rate of clearing due to immune function times how many infected people there are. So that's how many new susceptible people there will be who just got better. The number of infected individuals is going to go up by the rate of infection of susceptible people, and it's going to go down by all of these death rates times the number of infected individuals. Looks like a mess, isn't actually so bad, except because we've got this S times I, that makes it nonlinear, so it's our most complicated model of the day. It is a multivariable nonlinear model, because we've got multiple independent and multiple dependent variables, and it's nonlinear. It's a mess. But it's not so bad. I'm going to skip general solutions and go straight for the equilibria, because a lot of times, let's be honest, that's what we actually do. So to find the equilibria, same as always, we set ds by dt equal to 0 and di by dt also equal to 0. So that means 0 is equal to theta minus ds minus beta si plus gamma I, and 0 is also equal to beta si minus all of these death rates times I. And since this is by definition the equilibrium, I'm going to put hats on all of the s's and i's. So this stuff will all equal 0 when we're at the equilibriums for s and for I. So this looks kind of gross. I'm going to call this equation 1 and this one equation 2 so we know what we're talking about in a minute. So from 2, we can factor this a bit, and we can see that 0 is equal to I times beta times s minus all of the death rates. So that means I is equal to 0 is one of the equilibria. There's a possible equilibrium point. The other equilibria will happen when 0 is equal to all that other stuff, minus the death rates. let's look at this one. When I hat is equal to 0, what's s hat? So let's plug that back into 1. So from equation 1, we've got 0 is equal to theta minus ds hat minus bs hat. And I hat we decided was 0 plus gamma also times 0. So these two terms go away, which leaves us with theta minus ds hat equals 0, which means s hat is going to be theta over d. So we've got one equilibrium point, equilibrium 1, I hat is equal to 0, s hat is equal to theta over d. So this equilibrium, right, this is just where disease is absent. No one is sick. No infected individuals, and the number of susceptible individuals is just governed by how many new people show up and how many people die. So, as an exercise, and partly because I'm running out of room, find the other equilibrium. Because intuition should tell you the state where nobody is sick is an equilibrium. The state where everyone is sick is probably also going to be an equilibrium. It's just a bit of a hint. But by doing this same simple plugging things back into equations from 1 and 2, you can find the other equilibrium where I hat is not equal to 0. So what about stability? We have our two equilibria, the equilibrium where disease is absent and the equilibrium where disease is endemic. For what values of our parameters are those two equilibria stable? So what does it mean for the disease absent equilibrium to be stable? Well, imagine a world where no one is sick, and we suddenly introduce 1 or 2 sick people. Will the system go back to being disease-free, go back to the equilibrium point? If it does, that means it's stable. If it doesn't, that means the disease-free equilibrium is unstable. So in this case, what we want to know is what happens to our system if we're close to the equilibrium point, but not on it. So imagine we've started at the equilibrium and just gone a small amount away from it. So our initial value of s is going to be the equilibrium value of s plus some small error. We'll call it epsilon s. And our value for I is going to be I hat plus some small error, epsilon hat. Right, so these are both close to the equilibrium. And by rearranging those, I can say that epsilon s is s minus s hat, and epsilon I is I minus I hat. This is going to matter in a minute. So the stability of our equilibrium is dependent on the behavior of these guys, of the errors. If these are going to shrink, that means that the system is going to go back towards the equilibrium point and it's stable. If these are growing, that means the system is going to blow away from the equilibrium point. So what that really means is that we need to know the rate of change of our little perturbations, right? If these guys are less than 0, our system is going to be stable at that equilibrium. If they're greater than 0, it's going to be unstable at that equilibrium. So how do we get expressions for these derivatives? Well, if you think about it, the change in ES, epsilon s, is going to be the derivative of this thing, s minus s hat, at the equilibrium point. Well, the change in the equilibrium point at the equilibrium point is 0. So this is actually just ds by dt. So we can use our original equation for ds by dt to tell us about how this little error is going to change. And that means the other one, d epsilon I by dt, is d by dt of I minus I hat, which is just di by dt. Because d I hat at the equilibrium point is going to be 0. Since this is a nonlinear model, we can't just skip straight to the matrix and find the eigenvalues and be done. We're going to end up having to make a linear approximation to our system close to the equilibrium point. So I'm just going to quickly define my two functions here. D epsilon s is going to be some function f, and it's a function of s minus s hat and I minus I hat. And I'm going to define d epsilon I by dt to be some function g, which is a function also a function of s minus s hat and I minus I hat. This is just so I can use notation on the next slide. So these guys are both nonlinear functions. And if I want to use the matrix approach I used in the last example, I need to find linear approximations to both of these. So I'm going to use Taylor approximations to turn these guys into linear models so that I can use my matrix magic on them. So that means we're going to have to use a multivariate Taylor expansion, which you may not have seen before, but it looks an awful lot like the single variable version. So I'm going to say that my d epsilon s by dt is going to be equal to f that I just defined on the last slide at s hat and I hat at the equilibrium, right, at the equilibrium, plus the partial derivative of f with respect to s at the equilibrium times s minus s hat plus the partial derivative of f with respect to I at the equilibrium times I minus I hat plus a bunch of higher order terms. So this ugly business is just a Taylor approximation near the equilibrium point, s hat and I hat. So, since we're doing this near the equilibrium point, and we already defined, so this function was a function of di by dt and ds by dt, and both of those are 0 at the equilibrium point. Go back down here. This is going to be equal to 0 plus these partial derivatives at the equilibrium point. S minus s hat plus the partial derivative with respect to I at the equilibrium point times I minus I hat plus stuff we're going to ignore. That's a linear approximation, so we just get rid of that. So if I make a similar expression for d epsilon I, we can get back to a matrix expression where we say d epsilon s by dt and d epsilon I by dt is equal to a matrix of these partial derivatives. So for the top one, df by ds and df by di all multiplied by epsilon s, right, because this bit here, s minus s hat, is what the definition of epsilon s is. And this bit, I minus I hat, is the definition of epsilon I. So down here, this s minus s hat becomes epsilon s, and the bottom part of my matrix becomes dg by ds, right, because I defined this to be some function g, dg by di, all multiplied by epsilon I. So now we've turned our complicated nonlinear ugly problem into a linear problem that we can apply matrix algebra rules for. So, and the stability, because this is linear now, the stability criterion is the same. If we get the eigenvalues of this matrix, and they all happen to have negative real parts, then we know that this system is stable at this equilibrium point. So the only thing that really matters here, I'm going to call it J, is this matrix of partials. So this matrix of partial differentials is called a Jacobian matrix. And as a general rule for this kind of model, what you need to do is start by defining expressions for these epsilons, these deviations from the equilibrium, and find the eigenvalues of the resulting Jacobian matrix. A lot of times if you're reading papers and people talk to models, they just say, we have a system of nonlinear things, here's the Jacobian, boom, the eigenvalues were this, so it's stable. That's what they're actually doing when they just throw that in there. As a modeler, I actually went an embarrassingly long time without knowing what a Jacobian matrix is, so I'm going to push this point a little bit. If you have a bunch of functions, f1, which is a function of a bunch of x's, f2, f3, fn. You have a bunch of functions that are functions of a bunch of variables. The Jacobian matrix is all of the possible arrangements of partial derivatives. That usually goes df1 by dx1, df1 by dx2, df1 by dx3, all the way to df1 by dxn, and then down the rows goes df2 by dx1, all the way to df1, dfn by dx1. Then down here you'd have dfn by dxn. It doesn't have to be square, so I'll just say there's m x's rather. Anyway, so if you solve the values in this Jacobian matrix at the equilibrium point, and then you find the eigenvalues of that matrix, it tells you your stability with the same stability criterion. If the eigenvalues are all negative, it's a stable system at that equilibrium point. And if the eigenvalues of your Jacobian have complex parts, then there are cycles until you get to the equilibrium point. So for an exercise, you should finish the example I started. Right? Actually evaluate the stability of that epidemic model. So remembering that I defined d epsilon s by dt ended up being the same as ds by dt, and we just renamed it f as a function of s and I, which is a function of s and I, and d epsilon I by dt ended up being the same as di by dt, which we renamed g and called it a function of s and I. In order to find the stability, you're going to need the extra equilibrium that I asked you to calculate before, and you're going to evaluate the Jacobian matrix df by ds, df by di, and dg by ds, and dg by di, at I hat and S hat for both equilibria. So you'll end up with you should have two different equilibria, and you'll end up with two different results for your stability. And since we didn't give values to any of those variables, what you'll end up with is a set of conditions for stability. If theta and beta and all of these other things are greater than some value, the system is stable, and if they're less than, it'll be unstable. So in summary, differential equations aren't that bad. To find equilibria, set all of the differentials to 0. Stability, find the eigenvalues of either your Jacobian matrix if it's fancy, or your linear matrix if it's already linear. Negative real part of eigenvalues gives you stability. Complex eigenvalues give you cycles. I've kind of glossed over general solutions a bit, because that actually can be very fiddly, which is why there are entire courses on differential equations that take less than 1 day. So if you don't have a simple model and you do need to find a general solution, at least now you should have the vocabulary to recognize what kind of model you have, so you can go looking for the tools to find a general solution. And just as my personal recommendation for ease of reading and biological motivations and stuff, Otto and Day's textbook has several really great chapters about differential equation modeling in biology, so I suggest them as a first place to look if you run into trouble, and I'm not around to ask.